Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 25, Organic Chemistry 1. Today we will continue on chapter 7, Alkyl halides, Nucleophilic substitution, and elimination reactions. In the previous lecture, we covered second order nucleophilic substitution reaction, SN2. Today, we will talk about first order nucleophilic substitution reaction, and they call it unimolecular, SN1 reaction. The carbon ligand bond is cleaved independently, forming an anion nucleofuge and carbocation. Then nucleophilic attack on the carbocation to form carbon nucleophile bond. The rate of this reaction depends only on the substrate, has nothing to do with the nucleophile concentration. So the rate is equal rate constant K times the concentration of the substrate. Here we lose leaving group. Here we have nucleophilic attack reaction pattern. So we start with substrate, the leaving group leaving away from the R group, that's the transition state, and this step is a rate determining step, the high scene energy. Then the leaving group separated from the alkyl group, forming carbocation nucleophile approach to give second transition state, then close enough to form the bond and form our nucleophile, new compound product. Substituent effects. The rate limiting step of the SN1 reaction is the ionization to form carbocation and strongly endothermic process. The first transition state resembles carbocation Hammond postulate. Consequently, a rate of reaction depends strongly on the carbocation stability. The tertiary carbocation is the most stable due to positive inductive effect of the alkyl group, as well as hyperconjugation effect. So for SN2 reactivity, we will find out that tertiary is more reactive than secondary, than primary, than methyl halide. Resonance stabilization of the carbocation can also promote SN1 reaction. For example, allyl bromide, even this carbon is primary, Sp3 in the beginning, alkyl halide. Okay, for the alkyl halide it is Sp3 hybridized. When it's ionized, it's Sp2. Okay, so allyl bromide is primary halide, but undergoes the reaction about as fast as the secondary halide. Why? Because of the resonance effect. So we have two resonance structure forming a double bond here, and here single bond. To widen the view scope, SN1 reaction reactivity, tertiary, is more stable than secondary, which is almost equal in reactivity with benzylic and allylic. They are reactive than primary, and the primary is more reactive than the methyl. Vinyl and aryl halide do not react in nucleophilic substitution reaction. So we can reaction of vinyl chloride with nucleophile will not give the nucleophile displacement with the chlor. Again, chlorobenzene will not react with nucleophile to form a real nucleophile bond. If you compare secondary allele for reaction coordinate or reaction energy diagram, we will find that from a starting material needs higher activation energy to reach the first transition state. In the tertiary alkyl halide, the activation energy is smaller, lower activation energy. That's why the reaction of tertiary alkyl halide faster than the secondary alkyl halide. Example: heating tertiary butyl bromide in boiling methanol, methyl tertiary butyl ether can be isolated from the reaction mixture. We call this methanolysis. So the first step is loss of leaving group, formation of carbocation, then followed by nucleophilic attack lone pair of electrons from the oxygen of methanol to the carbocation, forming this oxonium ion, which upon proton transfer gives ether. Leaving group. Good leaving group should be weak bases, therefore they are the conjugate bases of strong acid. The hydrohalic acid like HCl, HBr, HI are strong acids, and their conjugate bases are all weak bases. Other weak bases such as sulfates, ions, sulfonates can serve as good leaving groups. For example, if you have OH alcohol, OH is bad leaving group. To make it a good leaving group, we add drops of acid to transfer it to oxonium ion. So the leaving group will be water, and water is a good leaving group. Or transfer OH to autosyl group, okay, by reacting with para-toluene sulfonyl chloride. Here we have good leaving group with negative charge, and the negative charge ion can resonate to stabilize this ion. So tosylate ion is better leaving group than iodide, than bromide, chloride, and the chloride is almost as good as water as a leaving group. Choose the member of each pair that will react faster by the SN1 mechanism. 1 bromopropane or 2 bromopropane. For the structure 1 bromopropane, this carbon, primary alkyl halide, so you expect to give primary carbocation. For this carbon, it's secondary, and we are expecting it to give the first step of SN1 mechanism, secondary carbocation. Secondary carbocation is more stable than primary carbocation. We're expecting the 2-bromo to be faster. 2-bromo 2-methylbutane or 2-bromo 3-methylbutane. In this case, the carbon here is tertiary and here is secondary. So which one is more reactive? Of course, 2-bromo 2-methylbutane. Okay, 1-bromo propane, this carbon is primary and will give primary carbocation. Here again, primary, but this is allylic carbon, and the allylic carbon will give allele carbocation, which stabilized by resonance. So this is more stable and will be faster for SN1 reaction as substrate. 1-bromo to 2-dimethyl propane or 2-bromopropane. Here is the carbon, will give primary carbocation, and here is secondary carbocation. Of course, secondary carbocation is more stable than primary, so 2-bromopropane will be faster. 2-iodo-2-methylbutane or tertiary butyl chloride. Here is tertiary carbocation, and this one will also give tertiary carbocation. But as you see here, leaving group here is iodide, a better leaving group than chloride. So which one will be faster? 2-iodo-2-methylbutane will be faster. Let's solve this question. 3-bromocyclohexene is secondary halide, and benzyl halide is primary halide. Both halides undergo substitution about as fast as most tertiary halides. Use resonance structures to explain this enhanced reactivity. For the 3-bromocyclohexene, this is secondary alkyl halide, but dissociation will lead to allylic carbocation, and allylic carbocation will stabilize via resonance. Okay? For the benzyl bromide, this carbon is primary alkyl halide, will form primary carbocation, but this is a benzylic carbocation which will stabilize by resonance by delocalizing the positive charge over the benzene ring, as seen in here. Motion of 2 electrons will form a double bond, and the positive charge will be on this carbon, moving these 2 electrons, okay, by clouds to form a double bond in here, and this carbon will carry the positive charge. Again, 2 electrons form a double bond, and here the positive charge. These 2 electrons will form a double bond in here, and the positive charge will be once again on this carbon. Solvent effect. SN1 reaction require highly polar solvent that strongly solvate ions. One measure of the solvent's ability to solvate ions is its dielectric constant, a measure of solvent's polarity. Hexane nonpolar, very small dielectric constant. Ether, 4.3. Hexamethyl phosphoramide, polar, 30 dielectric constant. Dimethyl formamide, 38. Dimethyl sulfoxide, 48. Ethanol, methanol, and water have good to very high dielectric constant. Water is the best. Looking for ethanol, methanol, and water, they are protic solvent. Hexamethyl phosphoramide, dimethyl formamide, dimethyl sulfoxide, they are polar, but they are aprotic solvent. They are aprotic solvents. Hexane and ether are non-polar solvent and they are aprotic solvents. From this data, okay, I can expect the water to be very good medium for SN1 mechanism, alcohols, methanol, dimethyl sulfoxide is good, dimethyl formamide is good, okay, and hexamethyl phosphoramide is good too. Experimentally, you can see that having tertiary butyl chloride, tertiary butyl bromide reaction with alcohols to form ether. If you run the reaction in ethanol, just only ethanol, the rate of the reaction is 1. Mix it with water, make it 140 to 60. Increase the percent of water 20 to 80 to 20, 14,000. If you just reacted with water, it's 100,000 faster to form the alcohol, of course. Note that ionization occurs much faster in highly polar solvent, such as water and alcohol. Although most alkyl halides are not soluble in water, they often dissolve in highly polar mixture of acetone, alcohol, and water. This slide showing how water facilitates the SN1 reaction via solvation of the transition states as well as the intermediate. So here in the transition state stabilization, and in this part the carbon sp2 carbon is stabilized via a partially negative charge of oxygen, and the halide nucleophilic is stabilized a partially positive charge of proton from water molecules. In this slide, reaction energy diagram showing the effect of polarity of solvent. So if you have a polar solvent, you will find that the energy of starting material lower than the energy in case of non-polar solvent, and again the transition activation energy to first transition state here 1 is less than the E2 in case of non-polar solvent. So in polar solvent, the transition state stabilization, we can say it's much higher than the transition state stability in non-polar solvent. Intermediate, in case of polar, it will be solvated more stable than that intermediate in case of non-polar solvent. Stereochemistry of SN1 reaction. SN1 reaction mechanism, the carbocation intermediate is sp2 hybridized, means that it is planar and nucleophile can attack the carbocation from either faces to give racemic mixture, both enantiomers. So if you have one stereogenic center in the molecule and you get an intermediate sp2 planar with enantiotopic faces, we will see that in this slide. Here we have sp2 hybridized carbon. It is planar with 2 equal faces, planar cation intermediate with symmetrical faces. So the probability of attacking the nucleophile from up or bottom will be equal. So we can get retention in configuration. The nucleophile will attach to carbon exactly from the same orientation of carbon X, or inversion the opposite side. If it comes from up, it will be retention. From bottom will be inversion. If it is 50-50, we call this a racemic mixture, a mixture of equal amount of enantiomers. Racemic mixture is optically inactive. If the alpha carbon is chiral and there is another stereogenic center in the molecule, a mixture of diastereomers is formed in a substitution reaction. Here we have two stereogenic center, one alpha carbon, it's number 2, carbon number 2, and another stereogenic center, carbon number 4. Of course, the reaction will take place on carbon 2, so we can see that carbon 2 retention and carbon number 4 still the same. Carbon number 2 inversion and carbon number 4 still the same. So we have here 2R, 4S, 2R, 4S. Then inversion 2S, 4S the same. What is the relation between 2R, 4S and 2S, 4R diastereomers? Only if you have single chirality center, you get a racemic mixture. Diastereoisomers are different compounds with different optical rotation. Let's solve this question. RR 1-bromo 1,3 dimethyl cyclopentane undergoes SN1 solvolysis upon heating in ethanol to give 2 diastereomers. Write a complete mechanism that shows all the steps leading to these products, specifically showing the stereochemistry at each step. The starting material has 2 stereogenic center at 1 and 3. So it's 1R, 3R. This is sp3 carbon. Dissociation or loss of leaving group will lead to the sp2 planar carbocation intermediate with unsymmetrical faces. The face up is not the same as face down. Face up will have the methyl group up, and down will have hydrogen. So the nucleophilic attack in the next step will attack the carbocation from up or from down. From up will form this oxonium ion. From down we will have this oxonium ion. Then proton transfer by another molecule of ethanol, taking the hydrogen out, leading to the formation of 2s3r, or if this one will be 1r3r, 1r3r and 1s3r are diastereomers. Rearrangement in SN1 reaction. Carbocations frequently undergo structural changes called rearrangements to form more stable ions. A rearrangement may occur after a carbocation is formed, or it may occur as the leaving group is leaving. Here we have the carbon carrying Br, reacting it with methanol, heat. The O-methyl or methoxy group will link to the same carbon so no rearrangement. On the other product, the methoxy now is attached to the adjacent carbon, to the original carbon. So in this one, product with no rearrangement. In this product, the product with rearrangement. The mechanism. Give the mechanism for this reaction. Okay. The first step, loss of leaving group. Formation of carbocation. The carbocation will be attacked, nucleophilic attack, by methanol molecule, forming this oxonium ion. Proton transfer to give the product with no rearrangement. Remember that this carbocation is secondary carbocation. If this hydrogen, carbon, hydrogen, electrons shifted with H, hydride shift to this carbon, tertiary carbocation will be formed. Tertiary carbocation is more stable than secondary carbocation. Then nucleophilic attack on this carbon, forming again oxonium ion, proton transfer to give the product with rearrangement. Let's solve these questions. Propose a mechanism involving hydride shift or an alkyl shift for each solvolysis reaction. Here we have alkyl halide. This is a carbon carrying the Cl. Alkyl halide on reaction with water and heat give the alcohols where the OH connected to the adjacent carbon to the original carbon Cl bond. So what happened in the first step? Losing, loss of leaving group, formation of secondary carbocation. Upon alkyl or methyl shift, the carbocation will be on this carbon, tertiary carbocation. Tertiary carbocation is more stable than secondary. Then this carbon will be attacked by the nucleophile water molecule, forming this oxonium, followed by proton transfer to give the final product. Reaction of iodomethyl cyclohexane with ethanol led to the formation of 1-ethoxy-1-methyl cyclohexane and ethoxycycloheptane mixture. This carbon is primary, and the first step will be loss of leaving group led to the formation of the primary carbocation, right? Primary cation is highly unstable. So what actually happened is the hydride shift takes place simultaneously with the loss of the iodide leaving group, or the alkyl migration will take place while the iodide leaving group is getting out. But to simplify it and see the clear picture, we'll say, okay, this primary carbocation formed. One of the pathways will be hydride shift. From primary, we'll get carbocation, tertiary carbocation intermediate, will be attacked, nucleophilic attack, by ethanol molecule to form oxonium. Deprotonation or proton transfer will lead to the formation of 1-ethoxy 1-methyl cyclohexane. On the other hand, alkyl migration will lead to the formation of cycloheptalium ion 7-member ring, which is secondary carbocation. Nucleophilic attack will lead to the formation of this oxonium ion. Deprotonation gave ethoxycycloheptane compound. See you in the coming lecture. Bye bye.